right, so here's our first reaction of alcohols, and it's a dehydration reaction. So what does that mean, dehydrate? We're removing water. What is one of the products? A water molecule. And how do we do this? We take an alcohol and we treat it with sulfuric acid and we heat it. That being said, what's actually happened here? What's changed? Well, the bonds we've broken include a carbon-oxygen sigma bond. So carbon-oxygen sigma bond. And we've also broken, if this product only has one hydrogen here, it used to have two hydrogens here, so we've broken a CH sigma bond as well. What have we formed? We formed a CC pi bond and a OH sigma bond. So in our mechanism that we're going to draw, we're somehow going to have to show all of those bonds breaking or forming. So how is that going to occur? Well, let's think about things a little bit. Sulfuric acid, what is that? Is that a base, acid? Where have you seen it before? Hopefully you are recognizing it as a strong acid. That is what it is. It has a pKa of around -3. We'll write that in here. So a pKa of about -3. So this is a really strong acid. So if that's a really strong acid, what is a proton acceptor, electron donor, on our molecule? So if we have sulfuric acid, and we're going to write it out right here, this is what sulfuric acid looks like. What can grab this partially positive? Remember, all these are polarized bonds. There's a partial positive there, a partial negative here. What on our molecule has electrons that would like to grab a proton? And hopefully what you're seeing and what you're writing down even without me telling you is that we need to find the partial negative over here. The partial negative would be on that oxygen. It's the most electronegative atom. It's got two lone pairs. So it is going to, its partial negative is going to be attracted to that partial positive, and we're going to get a proton transfer. And let's see if we can figure out what side this equilibrium will be on. So essentially we then have our protonated alcohol, and we have HO with all of the oxygen still on there, and just an O- on that oxygen right there. So what side should this equilibrium be on? And when we think about it, I just told you this pKa, it's not on our list, but it's -3. And what would be the most similar pKa to what we have here? Is water the most similar? Is hydronium ion the most similar? Something else? It should be hydronium ion, because hydronium ion has 3 hydrogens on it, so it's an oxygen of 3 bonds, just like that oxygen, and it's positively charged. And that pKa is -1.7. So these pKa's are pretty similar, but this is the stronger acid. So the equilibrium would be slightly, not a huge degree, but it would be at least somewhat to this side. Thinking about that again, why is this such a strong acid? Sulfuric acid is a really strong acid. We know that because I told you what the pKa is, but also strong acids have what? They have stable conjugate bases. Why is this a stable conjugate base? The negative charge is on an oxygen, that's good, but also it's not just on one oxygen, right? We can draw resonance structures, I'll do that over here, showing that essentially the negative charge, once we get deprotonation, is shared among 3 oxygen atoms, right? So not only do we have negative on an oxygen, but it's distributed over 3 different oxygens, and that delocalization of charge makes that a really stable anion. So that being said, this mechanism, what's going to happen, let's think about that for a second, and we're going to partially fill in just with our thoughts right now what's below on this course page. But essentially what we have here, H2O, is a really good leaving group. What made a good leaving group? A good leaving group is stable by itself, and we can know that it is stable by itself based on the pKa of its conjugate acid. So if we were to pull that water molecule away, that would generate a positive charge right here plus H2O. So was H2O a good leaving group? Well, what's its conjugate acid? Its conjugate acid is hydronium ion. Hydronium ion is a very strong acid. That means that water is really stable by itself. It's a really good leaving group. So essentially, this really wants to leave. We're showing it leaving by an E1 mechanism, right? It's this carbocation's forming, and then we're going to get the hydrogen pulled off. Does that make sense? So we get unimolecular reactions when we have a good leaving group and we do not have a strong nucleophile or base. Is there a strong nucleophile or base in these reaction conditions? No, there can't be, right? Because if a strong acid was mixed with a strong base, those two would just transfer a proton from one species to the other, and then the reaction would be like the acid would be all gone, no reaction would be able to occur. So we have a weak bases around here. We have no strong bases, so this has to occur by a unimolecular type mechanism. And at that point, the water molecule or the conjugate base, either of these really, can be shown to grab that proton from that beta position to generate the product alkene. So those are kind of the steps of this mechanism. It's basically an E1 reaction. These two steps look identical to an E1 reaction, but the only new thing is this first step. We have to protonate that alcohol because the alcohol by itself is not a good leaving group. It's only a good leaving group once it's protonated as water. So more on this once I erase some stuff. All right, so analyzing this reaction based on our previous ideas of elimination and substitution chemistry, essentially we formed a secondary leaving group. We formed a secondary leaving group, a secondary LG, this is it right here, in the reaction. And what we said about alkyl halides when they were secondary is they can undergo unimolecular or bimolecular reactions. It just depends on the identity of the nucleophile / base. So what kind of nucleophile / base do we have? We do not have a strong base / nucleophile. We do not have a strong base / nucleophile. So an E1 mechanism would occur. And for these reasons, secondary alcohols dehydrate via an E1 mechanism. So secondary alcohol, sulfuric acid, heat, those things together are going to provide an environment for an E1 type dehydration, which is a form of elimination mechanism. So yeah, that's that.